Hello everyone, and welcome to Unit 6. We had seen the first few chapters in Unit 6 earlier. So 6.3 polar coordinates represents our first new chapter in this unit. So we're going to introduce some different ways of viewing different types of numbers and quantities that we're more familiar with in other forms. So we're going to start here. This may seem suspiciously easy. We're going to plot the point 3, 4. What that tells us to do on a coordinate, our familiar coordinate grid, is travel 3 units to the right of the origin and then 4 units up. So our point, as you, I'm sure, know, would be located right here. This point is is found, as we said, by using a vertical and horizontal component. This, even though we don't really call it this very long, this system of graphing is known as the rectangular system. There are other graphing systems, both polar and parametric. We will see this year. Polar is what we're talking about today. The polar system is based on a horizontal ray that extends to the right, and I'll sketch this in as I'm describing it. A horizontal ray to the right and a terminal ray that is counterclockwise measured from that horizontal ray. So there is some angle where we start at our what's called the polar axis, that is here at the bottom. And this angle travels to what we call the terminal axis. The point that we've created, I'm going to put here in blue, is comprised of 2 different values. This point we'll call P is made up of r comma theta. Now, in our rectangular system, those coordinates x, y, x tells us how far to travel left, right or left, and our y, how much up or down. In our new system, we have new variables that we're using, r and theta. The r value is representing the distance from the central axis to the point itself. So this distance here, I'm trying to label it, is known as r. And theta, as you might imagine, is going to be represented by the angle here, right? This angle here. Just some additional details. This is known as the pole. I always kind of see this, and you'll see once we get into some graphs in our next set of notes, that it really reminds me of looking at like the top of a globe. Because what we'll see, our coordinate grid is no longer rectangular, but instead circular, almost like lines of latitude and longitude. So let's get some more details here. Polar coordinates are given in the form, as we said, r comma theta, where r is a directed distance from a pole, R kind of reminds me of a radius, and we could think about it very similarly, right? We know that the radius is the distance from the center of a circle to the edge, and similarly, this directed distance from the central pole will be our R value. This value can be positive. It can be negative. It can be 0. It's kind of rare that we'll see that, but we will see some examples of each. Theta is our angle to the terminal side. Similarly, we will have positive and negative theta values. Positive angles will be basically counted counterclockwise, and negative angles will be measured clockwise. Positive and negative basically just tells us which direction we need to follow, which we need to travel in order to arrive at that specific location. Once we get into some examples, I think you'll make more sense of what's going on. So here on example 1, we are plotting some coordinates here. Remember that these coordinates come in the form r comma theta. So that R value of 2 tells us that we are 2 units away from the central pole. So we are somewhere on this second ring, right, as we count out from the middle. And where on that second ring are we? Well, at 135-degree angles, starting here, right? There's 0 degrees. We know that this would be 180. If this is reminding us slightly of the unit circle, it should. Right, that's what these values that we've included here represent, right? 30, 60, excuse me, I made a mistake there. 30, 45, and 60. And, all the other values as we work our way around. Well, 135, we know that's in the second quadrant with a 45-degree reference angle. That point would fall right here. If we move over to another example, we can now see something a little bit trickier. We see that we now have negative R values and negative theta values. What that's telling us is, well, the negative one's not going to throw us off too bad. We do know that it will exist on the first ring around from the center, and it will occur somewhere. Okay, so let me explain what I mean by that. Negative 2 pi over 3, that shouldn't be too bad for us, right? If we have a negative theta value, that means we're traveling in the opposite direction. So pi over this would be negative pi over 3, and this next angle in the third quadrant would be negative 2 pi over 3. So that means that we are somewhere along this axis, and we are actually going to work in the opposite direction of where our angle seems to be located. Why is that the case? Because our R value is also negative. So rather than traveling 1 unit towards our angle in question, we're actually going to travel in the exact opposite direction. All right, that negative R value tells us to work in the opposite direction of the angle negative 2 pi over 3. So let's move on to page 2. In the rectangular coordinate system, there's only one representation of any point. In the polar coordinate system, there are actually an infinite number of ways to write the same point. So let's take a look at an example. Here they ask us to start by plotting the point 2 pi over 3. So we're going to travel 2 rings out at an angle of 2 pi over 3. Both of our values are positive. Now we can get to that exact same point on our polar coordinates with some other qualifications. So what do they ask us for? I'm going to try the first one on my own, and as we do with a lot of these videos, I'm going to have you try B and C on your own. So for part A, they tell us that R should be positive and that our angle should be between 2 pi and 4 pi. So with a positive angle, I started with a positive, an R value. I started with a positive R value, so it's going to remain positive. It's going to still be 2. When I want to change my angle but end in the same spot, hopefully you're thinking coterminal angles. So I'm going to add 2 pi to my angle. And if I add 2 pi to 2 pi over 3, the result is 8 pi over 3. Just to check that, if we were to go 8 pi over 3, this angle here would be 2 pi, if we traveled all the way around. And then if we keep going, an additional 2 pi over 3, we will be on this axis and with an R value of 2. As I said, I think our best move now is to pause. I'm going to pause the video, you should too, and try problems B and C. All right, let's see how we did. So here you can see that when I have an R value that's negative, the absolute value of that R value is going to be the same, right? It doesn't matter if we're traveling, forward along the axis or backward. The distance we're traveling from the central pole should be similar. So whenever we have these type of problems, our R value is going to have the same value, whether it's positive or negative, the same absolute value whether it's positive or negative for all examples. So with an value of negative R value, I basically need to figure out what angle is on the exact opposite side of the polar grid. In order to do so, I can simply add pi to 2 pi over 3 and find my angle. For the part C, I have a positive R value, so 2 is the obvious choice. And my angle should be between negative pi over 2 and 0. Well, what they're asking me to find basically is a coterminal angle, so I'm going to subtract 2 pi. So to find our way through all these problems, we're mostly going to be adding multiples of pi. I think I'm going to pause the video here. This is basically the intro to coordinates. The next part of this video will be dedicated towards converting between rectangular and polar coordinates.